All right. So the last speaker we had in our session is Mark Sutherland, who received his PhD from EPFL in 2022. He was co-advised by Babak, Falsafi and Alexandros Daglis at Georgia Tech. His work focused on data center network protocols, communication stacks, and microsecond scale software. Currently, he works at Oracle in Zurich, contributing to the MySQL Heatwave in-memory analytics accelerator and its migration to AWS. And he's presenting the work that is titled Cooperative Concurrency Control for Write-Intensive Key-Value Workloads. Go ahead,
yes.
Mark.
Okay, thank you everyone. Welcome, thanks for coming to my talk. As Sergey introduced, my name is Mark, and I'm presenting our work that was the last paper that I did before I joined Oracle. This was done with my advisors Babak and Alex. So as I'm sure most of you know, in-memory key-value stores are still a backbone of the online services that we all rely on today. And principles from seminal key-value store designs like Mica, like Memcached, and others are still prevalent in both practice and academic citation. But emerging workloads are really challenging the assumptions on which key-value stores are often built. So specifically, about 30% of workloads that Twitter recently published in OSDI are considered to actually be write-intensive. And an example of such workloads would be an online service that, for example, creates and then hydrates objects in memory before they're read by users. So it's really the prevalence and the evolution of these these new key-value workloads that mandates us to rethink key-value store design principles. And the problem that we specifically go after in this work is that state-of-the-art approaches in key-value stores, and particularly concurrency control, they generate load imbalance. This is because the current wisdom is that you can freely balance reads across threads, like these ones, but writes are statically partitioned across threads to simplify concurrency control. So in this example, these writes have to be assigned to the top thread, which is blue, because it's handling all partitions colored blue. In this case, all other threads are actually idle, and that's wasting an expensive server CPU. So although this kind of partitioning is really good to boost throughput, it really removes any possibility to do write load balancing by design. And in our work, we propose to address this problem by dynamically partitioning the key-value store at runtime. A dynamically partitioned key-value store is capable of assigning different colors to these two writes if they access different partitions. That allows them to be processed independently. And we show that such dynamic partitioning allows us to both load balance writes while maintaining this lightweight concurrency control from prior work. And that allows us to really boost performance. So having introduced our work and kind of told you about our main result, I now want to start by explaining the insights we get from modern key-value workloads and how that influences the design of our key-value store, which is called C4. So to intuitively understand these workloads, we're going to categorize them in this 2D space that you see here. And the axes of this space are the skew distribution of the workload on the X and the amount of writes in the workload on the Y. And modern workloads diverge from canonical ones into kind of two common classes that you see. On the top left, you have those that are write-dominated, so 60, 70, 80% writes, but they're mainly uniform distribution. And then on the bottom right, you see workloads which are read-dominated as before, but they have extreme popularity skew, much more than we've considered in prior work. And when the key-value store uses a concurrency control policy that's called concurrent read exclusive write, you'll hear me call that CRU, both of these workloads exhibit load imbalance for the same reason. For the first class, it's kind of what I showed you before in the introduction, right? We just can't balance these uniform writes across threads because we're not allowed to do it because of CRU. And in the second case, even though the workload is read-dominated, there's so much skew that the amount of writes just overwhelm the hottest thread. And furthermore, the read-write conflicts, because of the skew, are very, very common. So because we observe that CRU is the common problem for both of these workloads, we need a common insight that allows us to address both of them with the same improvements. And our insight here is that if we know in advance or at runtime which writes are actually going to conflict with each other, that's sufficient information for both of these workloads. And to explain this, consider this key-value store that you see here. We generally spread partitions across threads using something like hashing or sharding. So similar to the example we showed previously, these two incoming writes should go to the top thread, T1, because they're both blue. But now consider that we reveal that these writes are to actually different underlying partitions, like P1 and Pn. What that means is that they can be processed by independent threads, because when they run, they'll access disjoint sets of the key value store, and there's no need for them to ever synchronize. So it's this knowledge of which partitions that the writes are actually accessing at runtime that will allow us to restore a lot of that flexibility and load balancing we lost. So what should we do about the other class of workloads, the ones that are very heavily skewed in read-write? Well, the right way forward in this case is we need to accelerate that overloaded hottest writer thread. This is actually also possible if we have the knowledge of which writes are truly conflicting. So consider, once again, this key value store you see here. There's two writes incoming to it to key A, and thread 1 needs to be the one to process those incoming writes because it's already updating that partition. Load balancing these writes is not going to help us because other threads will simply have to acquire locks, and we're wasting those threads again. And what we observed is that as this thread gets assigned more and more conflicting writes, basically a natural batch starts to be formed in its input queue. So it's logical that if the thread knows and has the knowledge that it is about to process a bunch of conflicting writes, it can compact all of those writes together into one single update that it writes to the key value store. And this is beneficial for both the reader and all the other writers, the writer and also all the other readers in the system as well, because the readers are now accessing a partition that has much less update load. So once again, it's the knowledge that the thread has to have that it's about to process a bunch of conflicting writes that is going to allow us to boost both reader and writer throughput. And those two techniques that we just presented are what make up the dynamic crew, or you'll hear me call it D-crew, concurrency control policy in C4. D-crew only maintains exclusive access for the partitions that are actively being written by threads, not all partitions at all times. So in this graphical example, only partition N is considered to be in exclusive mode because T2 is writing it. And as you can imagine, to enforce this kind of dynamic mapping of partitions to threads, we need to introduce some state into the system. So C4 utilizes a table, a partition map, that simply stores which partitions are being mapped to which threads. And we also have to add some kind of D-crew unit to enforce those mappings. So let's see how this works. Consider we have our two writes that I've been showing before arriving at this D-crew unit. The D-crew unit then has to look up that table to see if there's any specific mapping that's existing for those partitions being accessed. In this case, you see that partition N has to be sent to thread T2 because there was already a mapping in the table. But partition 1 was completely free. We could send it to any thread. So with the same hardware and the same unit, we've done both write balancing of independent partitions, and we've created compaction opportunities. You can see the writes getting assigned to threads, and now we see that thread 1 has actually kind of gained an exclusive mapping while it's processing this write to the partition that we sent to it. So this D-crew policy is enough for us to improve both kinds of write-intensive workload. Now that you've kind of seen the insight of our work, how do we actually realize this? What do we do for our key value store C4? Well, we implement D-crew in the server NIC. And we do this by enhancing a prior design which already kind of achieved load balancing in hardware. And we chose to do D-crew in hardware because the request rates you can attain with a modern key value store running on a many-core server are simply too high to have one software thread be your load balancer. You'll simply overrun it. It will not be able to keep up. So what we do is we simply add this partition map to the NIC's hardware state, and we add some surrounding logic to look up that map and enforce D-crew like I showed you before. In contrast, we implement request compaction in the key value store software. So our design adds a very thin software layer inside the key value store that allows it to look a few entries ahead in the queue of requests that it is about to access and determine if there are true conflicts in that queue. And if so, the thread compacts those writes together and writes them to the data store at one time. I want to emphasize that both of these changes are very limited in complexity. They're roughly equivalent to adding one TLB to a whole server and 100 lines of code to the key value store. And we think these are very modest for the performance benefits that they enable. I want to now present one evaluation highlight before we conclude. So we evaluated C4 with cycle-accurate simulation, and we used the full-scale 64-core socket. You can look at the microarchitectural details of our work in the paper if you're interested, but here I just want to call out two things. I want you to notice that we only used a very, very small partition map for our decrew policy of 96 entries, and this keeps it very fast to look up and very easy to manage. And second, the key value store workload that I'm going to show you is kind of in the top left of that space that I showed you before. So it's a mainly uniform workload that's write-dominated. And we use the Mica key value store as our baseline, and we implement crew on top of it, which is the baseline that I showed you before. We're also going to compare against the concurrency control policy called ERU, or exclusive read, exclusive write. And we compare against that because it partitions all requests, reads and writes, and it's said to create better locality. So we want to compare against that as well. Then we have decrew, which is what's done by C4. And we're also going to show an ideal bound that we can attain in the system, which is simply a read-only workload because it has perfect load balancing flexibility and no synchronization. The highlight I want to show you is to focus on the tail latency benefits of decrew. So in this graph, you see the load applied to the server on the x-axis, and then on the y-axis, you see the 99th percentile latency of the key value store's responses. And we're going to cut this graph. We're going to use a tail latency objective of 10x the average service time, which is very common to do in the literature. The first thing I want you to see is that despite the fact that ERU has no synchronization between threads required, it actually has the worst performance of any system we evaluated because there's no load balancing flexibility. And the 99th percentile latency degrades quickly. Now, when we compare crew against decrew, with only 50% writes, decrew gives us about 1.3x better tail latency. Now, this is not really a challenging write-dominated workload, so we also show one that has 85% writes. And this is where decrew really starts to shine. We get about 5x better 99th percentile latency than the current state of the art under a higher absolute load being applied to the server. I also want to point out that decrew tracks that ideal line that you see almost up until the saturation load, where it starts to slightly diverge when we get some write conflicts. So decrew provides almost near ideal performance right up until when the server is becoming overloaded. And I want to conclude this talk by reiterating that these emerging write-intensive workloads require a key value store design update. And specifically, we want to restore the load balancing capability that we lost for writes by partitioning them across cores. And our contribution to this end is dynamic write partitioning, and we called it decrew in our work. And then we implemented our key value store, C4, which is able to distinguish which writes are truly conflicting. C4 gets better 99th percentile latency and higher throughput than existing systems, which as a result, I'll leave you to the paper to see, with all of these other points that you can see also contained in our paper. Thanks for your attention, and I'm happy to take your questions now.